In this video and in the next 7 videos, we will be talking about second-order linear differential equations. To introduce how important they are, linear differential equations of second order are vital to any investigation of the classical areas of mathematical physics. They show up in fluid mechanics, heat conduction, wave motion, and electromagnetic phenomena. We will start this video by introducing the general second-order differential equation. Then we'll look at linear second-order differential equations, compare that to nonlinear second-order differential equations, and then limit our scope to linear second-order homogeneous differential equations. And then finally, we are going to solve the linear second-order homogeneous differential equation with constant coefficients, and they have this form ay double prime plus by prime plus cy equals 0. And when we solve the second order homogeneous differential equation with constant coefficients, we will come up with a general strategy or method of solving it, and we will do a few examples. We will begin by defining what a second-order differential equation is. In this case, a second-order differential equation is an equation for the second derivative of a function y, and it's a second derivative, hence the name second order. So it's an equation of the second derivative of a function y, and it's equal to a function that's dependent on the value of t, y, and dy dt, the first derivative. We will narrow down our investigation into linear second-order differential equations. So those are our second-order differential equations where y and dy dt are linear. So in other words, we can have a function of t, y, dy dt, so we can have, which is equal to a function of t by itself minus a function of p of t multiplied by dy dt minus a function g of t multiplied by y. And you can see the y is raised to the first power. There's no other exponent on y, and y is also not a function of something else like e, so it's not like e to the y, it's not sine of y, it's just plain y. Similarly, for dy dt, you don't have any powers associated with this. This is only to the first power. There are no negative exponents or positive exponents, and there's nothing that dy dt is a function of, so it's not like sine of dy dt. It is just dy dt. So when these two are linear, y and dy dt, when these two variables are linear, we consider the equation, the second order differential equation, to be linear. Sometimes we write this function as y double prime plus pt of y prime plus qt of y equals g of t. And note, so if you have some function of t in front of y double prime, you can just divide everything, the whole equation, by whatever is in front of y, and you get this form here. We will also look at initial value problems. In this case, the initial value not just tells you the initial, like a point, t naught, y naught, that we start at, but also it tells you the starting slope. It tells you the slope at the point t naught, which is essentially what is described here. The initial value problem not only identifies a particular point t naught, y naught through which the graph of the solutions must pass, but it also identifies the slope y naught prime of the graph at that point. Then, of course, we have nonlinear second-order differential equations. Analytic investigations of nonlinear equations are relatively difficult, and for that reason, often in a first differential equations class, we only look at numerical, so sort of like what we did with Euler's approximation. So we only look at numerical or qualitative approaches. A qualitative approach like those qualitative graphs we did for some first order differential equations. So we either look at numerical or qualitative approaches, not the quantitative solving of the solutions. But that's okay, because as we mentioned, there are several very important applications of the linear second order differential equations, which were mentioned in the introduction. So it's not just a simplification that we're studying these linear second order differential equations. They are valid and important in their own right. Initially, we're going to focus on linear second order homogeneous differential equations. That is of the form where your differential equation is equal to 0. That is a function of t times y double prime, a function of t times y prime, plus a function of t times y is equal to 0. This equals 0 is what makes it homogeneous. So a second order linear equation is homogeneous if g of t equals 0 in this equation here. If g of t is non-zero, the equation is called non-homogeneous. And g of t is sometimes called the forcing function because many applications the g of t describes an externally applied force. But don't worry about the fact that we've simplified this. It feels like the whole time here we've gone from general, we simplified once, we simplified another time. Even though we've simplified the homogeneous equation, if we wanted to solve a non-homogeneous equation, the first step is to solve the homogeneous equation. So this will get us along the way to also solving non-homogeneous equations. And one more simplification. I know it seems like we've gone from general second order differential equations and we keep simplifying it to linear second order differential equations to linear second order homogeneous differential equations, and now linear second order homogeneous differential equations with constant coefficients. So this is the last simplification for this video. So, and actually the last simplification we'll do. Other videos it'll become more advanced. So instead of a function of t multiplied by y double prime, a different function of t multiplied by y prime, and another function of t multiplied by y, we're just going to have constants. So we have constants a, b, and c. So we have the general form of this linear second order homogeneous differential equation with constant coefficients is a y double prime plus b y prime plus cy is equal to 0. It is kind of funny because it took almost an entire page to go from this general form to the form we're going to be working with in this video. So before solving the general equation y double prime plus by prime plus cy equals 0, we're going to take a look at a simple example to get some clues. So our simple example is y double prime minus y is equal to 0 with initial values y naught is equal to 2 and y prime naught is equal to -1. And just a note, in this general form of a y double prime plus by prime plus cy equals 0, for this equation here, y double prime minus y equals 0, we have a equal to 1, that's our coefficient from in front of y double prime, b is equal to 0 because there's no y prime in here, and c is equal to -1, that's the coefficient in front of the y term. Now, just looking at this equation, I can rewrite this y double prime minus y equals 0 as y double prime equals y. And so our question is, what function from calculus does y double prime equal to y? And the answer is e to the t. And because this is a double prime, also e to the minus t will work. And you can try it out. Y prime of y2 prime would be minus e to the minus t, and then y2 double prime would be e to the minus t. More general, you can multiply y1 and y2 by any constant. So c1 e to the t is a solution, as well as c2 e to the minus t. Now, even more generally, any linear combination of y1 and y2 will solve this equation. So in other words, y1 is equal to c1 e to the t plus c2 e to the minus t will solve this equation here. And you can verify that. If I take y prime, I'm going to get c e to the t, and then minus c2 e to the minus t. Now y double prime, I get back c1 e to the t plus c2 e to the minus t. Since the coefficients c1 and c2 are arbitrary, this solution for y represents an infinite two-parameter family of solutions of the differential equation. So in other words, you can pick an infinite number of values for C1 and fix C2 to some one value, and you'll get an infinite number of solutions. Or you can fix C1 and then take any value for C2 and you get another whole set of infinite solutions. And of course, just like in our first order differential equations, it's the initial values that will pick out particular solutions. So using the initial value, y0 equals 2. So in other words, 2 is equal to, plugging in 0 here, I get C1 plus C2. Using my other initial value, y prime of 0 is equal to negative 1. So I calculated y prime is equal to C1 e to the t minus C2 e to the minus t. Plugging in 0, so this becomes 1, this becomes 1. I get, and plugging in 0, I get negative 1, and I'll have C1 minus C2. So these two equations, minus 1 equals C1 minus C2, and also 2 is equal to C1 plus C2, will give me C1 is equal to 1/2 and C2 is equal to 3/2. So my general solution is y equals 1/2 e to the t plus 3 over 2 e to the minus t. And hence we have solved our differential equation. Again, you can test this by taking the first derivative and then the second derivative, and you will see the second derivative minus y will equal to 0. You can also plug in 0 into this equation and you will get 2. And if you plug 0 into the derivative, you should get negative 1. Now I've kind of grouped everything and moved it over a little bit, shrank it down a little bit so we can make some notes. And that there were two key points that we're going to use when we try to solve this equation here, the linear second order homogeneous differential equation with constant coefficients a y double prime plus b y prime plus c y equals 0. So the first key is that e to the t satisfies y double prime equals y. The second key is once we identify solutions, in this case we had identified two solutions, e to the t and e to the minus t, we're going to use a linear combination to solve the initial value problem. In other words, we took a linear combination of our two solutions, so we had y equals c1 e to the t plus c2 e to the minus t. I have moved my two keys to solving that differential equation right here, and now we are ready to look at solving the general equation a y double prime plus b y prime plus cy equals 0. That's the linear second order homogeneous differential equation with constant coefficients. So the first thing we're going to do is assume our solution is of the form y equals e to the rt, just because we saw that et satisfies y double prime plus y. And we generalize this with a coefficient rt. So our y prime is going to be equal to r e to the rt, and our y double prime will equal to r squared e to the rt. The second thing we're going to do is substitute our y prime, and our y double prime into our equation a y double prime plus b y prime plus cy equals 0, and we will get our a and then our r squared, where's our y double prime? R squared e to the rt plus b, and then our y prime, r e to the rt plus c, and then our y, e to the rt equals 0. We can factor out the e to the rt, and we get a r squared plus br plus c equals 0. To solve this equation, since it's a product of two numbers equals 0, one of these numbers has to equal to 0. However, e to the rt is not going to equal to 0, so it must be this quadratic here that's equal to 0. So this equation here, the a to the r squared plus br plus c, is called the characteristic equation. And since it's equal to 0, we're going to solve the characteristic equation, and we'll find what r is, and then we'll plug in that r into our equation for y. So we'll have y1 is equal to e to the r1t, and y2 is equal to e to the r2t. So you can see I'm expecting two roots since this is a quadratic. It is possible we'll have two of the same roots, or we'll have a complex root, and those are things we're going to cover in other videos, but for now we're going to assume we have two distinct real roots, r1 and r2. So here are our two solutions, and then our second key is that any linear combination of these two solutions should help us, should be a solution. So I'm going to write y is equal to c1, the first constant, times y1, which is e to the r1t, plus c2 times y2, which is e to the r2t. So this is our general solution. We can plug in initial values to solve the initial value equation. And here you can actually solve it, in this form and get equations for C1 and C2, but I wouldn't memorize this. I wouldn't even memorize any of this. I would just kind of start here and just know to substitute into the equation and solve the characteristic equation, etc. So I wouldn't really memorize much other than this e to the RT part. Because all the rest of these calculations, I mean, you saw in our example how easy it was to figure out C1 and C2. It's pretty simple algebra. Here I just typed up what I had written before as kind of our method of solving this general equation, ay double prime plus by prime plus cy equals 0. The first step is to assume the solution is going to be of the form y equals e to the rt. Then you can calculate y prime and y double prime. You're going to plug in your solution y equals e to the rt as well as y prime and y double prime into your equation ay double prime plus by prime plus cy equals 0. Then you're going to factor out the e to the rt and you're going to solve the characteristic equation ar squared plus br plus c equals 0, and you should get root 1 and root 2, which then we will use to form our solutions y equals e to the r1t and y2 is equal to e to the r2t. Our general solution is going to be a linear combination of y1, y2. So we have c1 e to the r1t plus c2 e to the r2t, and then we're going to plug in our initial values to solve the initial value problem. A couple of notes. First, again, you can verify that these solutions were correct by taking y1, y2, taking the derivatives, plugging it back in the equation. You can see it'll be satisfied, as well as taking the initial conditions, seeing it will be satisfied. The second note is that this form here, the y equals c1 e to the r1t plus c2 e to the r2t, encompasses all possible solutions to this differential equation. Much like in first order linear equations, there's a general solution that encompasses all the solutions. So if you recall, for first order nonlinear equations, you could solve and get a form with c's, y equals c and then something, that actually could miss some solutions. In this case, it's linear. It will not miss any solution, so this is the general solution. So at least for cases which the roots of the characteristic equation are real and different. So there are two roots, two unique different roots that are real. So therefore, we can call this equation here the general solution. So I have moved our method of solving these differential equations here, and I have another example. Solve y double prime plus 5y prime plus 6y equals 0 with y naught equals 2 and y naught prime equals, or y prime naught equals 3. So first step, we assume our solution is of the form y equals rt. So I have y equals rt, I wrote out y prime and y double prime. Second step, plug in our y prime and y double prime into our equation. So plugging in y into this equation, y prime into this equation, and y double prime into this equation, I get y double prime is r e to the rt plus 5y prime, which is r e to the rt, plus 6y, which is e to the rt. I factor out my e to the rt, and I get my r squared plus 5r plus 6, which is equal to e to the rt, r plus 3, r plus 2 equals 0, which gives us r1 is equal to minus 3 and r2 is equal to minus 2, which means our first solution is y1 is equal to e to the minus 3t, and our second solution is y2 is equal to e to the minus 2t. These are our two solutions. So our general solution is a linear combination of our two solutions. So y is equal to c1 e to the minus 3t plus c2 e to the minus t2 t. And this is our general solution here. Then last, we can plug in initial values to solve the initial value problem. So y naught is equal to 2. So I have y naught is equal to 2. So if I plug in 0 here, this becomes 1, this becomes 1, and I get c1 plus c2. Then I plug in 0 into y prime, and I should get 3. So y prime, taking the derivative, is minus 3c1 e to the minus 3, minus 2 e to the minus 2. Plugging in 0, this goes to 1, this goes to 1, and I get y naught is equal to, here is equal to 3 from my initial condition, is equal to minus 3c1 minus 2c2. There should be a c2 here, pretend there is. And then solving our two equations, we get c2 is equal to 9, c1 is equal to negative 7. Plugging in, I have my general solution here. And I have it graphed over here for you. If I wanted to ask to find the maximum of y of t, so I have my graph of y, here's my maximum. It's just like we did in first year calculus. We set the derivative equal to 0. So y prime of t, here's my y. So taking the derivative, I'll get 21e to the minus 3t, and then I'll have minus 18 e to the 2t is equal to 0. To solve this, I'm going to multiply both sides of the equation by e to the 3t, so I get 21 minus 18 e to the t. So what I have is e to the t is equal to 21 over 18, which is 7 over 6. So t is natural log of 7 over 6. So this is the time over here where y reaches the max. So I plug in the time into my function y, and I get 2.2041. Time for another example. Solve 4y double prime minus 8y prime plus 3y equals 0, where y naught is equal to 2, and y prime naught is equal to 1/2. I start by assuming my solution is of the form y equals e to the rt. I calculate y prime and y double prime. Then I plug y prime, and y double prime into my equation. I get 4. Y double prime is r squared e to the rt. Minus 8 times y prime is equal to r e to the rt, plus 3 times y, which is e to the rt. I factor out my e to the rt, and I get my characteristic equation, 4r squared minus 8r plus 3. And again, this whole equation is equal to 0. So since this is not equal to 0, it must mean my characteristic equation is equal to 0. Solving for the roots, I use the quadratic formula, and I get, is that what it's called, the quadratic formula? Yes, it is. Okay, I get r1 is equal to 3/2 and r2 is equal to 1/2. So my general solution is equal to c1 e to the 3/2 t plus c2 e to the 1/2 t. Now to solve for the initial values, I use my initial value y naught equals 2. So plugging in 0 into here, this becomes 1, this becomes 1, so I get 2 is equal to c1 plus c2. Y prime of t, taking the derivative here, I get 3/2 c1 e to the t plus 1/2 c2 e to the 1/2 t. Plugging in 0 for t, I get 3/2, I get 3/2 c1 plus 1/2 c2, and also when I plug in, my final value should be 1/2. So I have this equation here and this equation here for c1 and c2. Solving those, I get c2 is equal to 5/2, c1 is equal to negative 1/2, plugging back in, so I have y is equal to negative 1/2 e to the 3/2 t plus 5/2 e to the 1/2 t. To review, we've talked about what a second order differential equation looks like. That is an equation that relates a second derivative to a function of t, y, and its first derivative. Then we looked at linear second order differential equations. They're equations of this form that are linear in y and dy dt. So in other words, we can have a function of t, and then we can have a function of t times dy dt plus a function of t times y. So the exponent on dy dt and y is just 1. We don't have any negative exponents. We don't have any powers of 2 or 3 or something higher. And dy dt and y are also not inside other functions like sine. So we don't have sine of y or e to the dy dt. We just have plain dy dt and y. So that is what makes this a linear second order differential equation. So again, f is linear ny and dy dt. gt, p of t, and q of t here are functions of t only and do not depend on y. Sometimes this linear second order differential equation is written in this form: y double prime plus p of t times y prime plus q of t y equals g of t. And then we also have initial value problems where we specify y t of naught is equal to some value, and also the derivative y prime of t naught is equal to some initial value. So the significance of this is the initial value problem does not only identify a particular point, t naught, y naught, through which the graph of the solution must pass, but it also identifies the slope, y naught prime, of the graph at this point, t naught, y naught. We briefly mentioned that if we had nonlinear second order differential equations, those are difficult to solve, and often explicitly solving them is not covered in a first-year differential equations class, but we will look later at numerical approximations and also qualitative graphs of these nonlinear second-order differential equations. We will cover linear second-order homogeneous differential equations, which is where we set our differential equation equal to 0. So second-order differential equation, linear differential equation is homogeneous if g of t equals 0 in the form of p of t y double prime plus q of t y prime plus r of t y equals g of t. So again, setting it equal to 0. And if g of t is not 0, it's non-homogeneous. And even though this seems like just yet another simplification, it kind of really is an important one to do, because the first step in solving a non-homogeneous equation is to solve, here it is to solve the homogeneous equation. But in this video, we further simplified and said instead of the p of t times y prime and then q of t times y prime plus r of t times y, we're going to replace these functions of t with constants a, b, and c. So we solved linear second-order homogeneous differential equations with constant coefficients a y double prime plus b y prime plus c y equals 0. And when we solved this equation here, our a y double prime plus b y prime plus c y equals 0, we came up with a general method for solving these equations, and we did a few examples. So that's it for this video. Thank you for watching.